power dividers are circuits which divide the power from the input port to many other ports. In the basic form, the power divider will divide power from the input port to at least two different ports. So we'll start with that type of power divider. Then once we know what it is, one can extend it to a number of ports. So we'll divide power from at one port. Input is given at one port. It is divided between two different ports. That is what we are going to see. So by definition, the power divider is used to split a signal. The signal contains power. So look at the top figure. There are two figures here. Look at the top figure. P1 is the total input power to the divider, and P2 and P3 are the output from the divider. P2 is equal to alpha times P1. Then P3 will be 1 minus alpha times P1, assuming that the divider is lossless. There is no loss in the divider. Then the total power output should be equal to total power input. If there is some loss, then the output will be less than the input power. We will consider lossless case. The opposite of the divider is the coupler. So suppose you have two input ports, P2 and P3 are two input ports. There we give power. Then at P1 we get the output. Then P1 will be equal to P2 plus P3. If P2 is the power at port 2, P3 is the power at port 3. Then it is called a coupler or a combiner. So coupler is used to combine a signal, combine different signals, whereas a divider is used to split a signal into two parts. These examples that we are seeing are three-port networks, because port 1 is P1, at port 2 we get power P2, at port 3 we get power P3. So there are total 3 ports, so it is a 3-port network. We are going to consider this 3-port network in today's lecture. If we have a 3-port network, then its S matrix will be of this form: S11, S12, S13, and S21, S22, S23, S31, S33, S32, S33. It is a 3 cross 3 matrix. The S matrix of a 3-port network, as you know, is a 3 cross 3 matrix. So the S matrix will be in this form. Our job is to find out what will be components or elements of the S matrix. Once we know what is a power divider, for different power dividers, we have to find out the components or the elements of the S matrix. S matrix will be a 3 cross 3 matrix. Now, when we consider the S matrix, we know there is some property, there are properties of S matrix, those which are to be satisfied. Suppose all the 3 ports of the network are matched and the device is reciprocal as well as device is lossless. If all ports are matched, which means S11 is equal to 0, no reflection, S11 is reflection coefficient, S22 is reflection coefficient at port 2, S33 is reflection coefficient at port 3. These are matched means there is no reflection. If there is no reflection, then S11 is equal to S22 is equal to S33 is equal to 0. 0 implies no reflection. It is reciprocal. A matrix is called reciprocal. Suppose you have a M cross N matrix, then the matrix is called reciprocal if AMN is equal to ANM. So on the elements S12 is equal to S21. So that way we have written the matrix. Now S21 is written as S12, S31 is written as S13 because of reciprocity. Similarly, S32 is written as S23 because of reciprocity. So the S matrix is now this 0, S12, S13, S12, 0, S23, S13, S23, 0. This matrix, once you represent a matrix in this form, this matrix is called an unitary matrix. This form of a matrix is called an unitary matrix. Now, we have now three elements. These three elements are distinct. What are the three elements? S12, S13 and S23. These are the three elements in the S matrix. These three elements are repeated. Such a device, as you know, based on the property of S parameter, a device or a network which is matched, reciprocal and lossless is impossible to realize. Physically, we cannot realize a device which is matched, reciprocal and lossless. Let us see that. We'll see it in the next slide. But from this, we conclude that if we want to match all the ports, all three ports, then we have to have either a non-reciprocal device or a lossy device. Here we will have a lossy device instead of a non-reciprocal device. We will prefer a non-reciprocal, reciprocal device. Now, let us prove that it is not possible to have lossless, reciprocal and matched lossless reciprocal device. So if you have a matched lossless reciprocal device, the S matrix is given at the top. Now losslessness implies that S matrix is unitary, that we have seen. Now if S matrix is unitary, then the top row, if you square the elements of top row and add them, that will be 1. Square the elements of middle row, add them, that will be 1. Square the elements of bottom row, add them, that will be 1. So S12 square, actually you take the amplitude. So S12 amplitude square plus S13 amplitude square is equal to 1. S12 amplitude square plus S23 amplitude square is equal to 1. S13 amplitude square plus S23 is equal to 1. So that is condition 1 because of unitary matrix. Then condition 2 is S13 into S23 star will be equal to 0. S23 star means conjugate of S23. So S13 multiplied by conjugate of S23 is equal to 0. S12 multiplied by conjugate of S23 is equal to 0. S13 multiplied by conjugate of S13. S12 multiplied by conjugate of S13 is equal to 0. Now what does this imply? This multiplication is equal to 0. This implies that at least two elements out of S13, S12 and S23 must be 0. At least two elements will be 0. If only one is 0, if or none of them is 0, then we cannot satisfy the three conditions. Suppose S13 is 0, only one is 0. Then the first one is satisfied. The second one will not be satisfied, and the first one and second and last one will be satisfied. Second one will not be satisfied. If none of them is 0, none of these will be satisfied. So at least two of these has to be 0. Now if at least two of these has to be 0, then only one of them will be non-zero. If one of them is non-zero, then the condition of adding these squares of amplitude is equal to 1 will not be satisfied. All the three conditions of adding them will not be satisfied. That implies that it is not possible to have lossless, reciprocal and matched at all ports. It is not physically possible. Mathematically or analytically we have seen this. From this, when you studied S parameters in your first semester, you must have seen this. Detailed proof you would have seen. Now let us consider a power divider, a real power divider. You can see the figure here. In the figure, we have a transmission line whose characteristics impedance is Z01. That is the blue transmission line, the left hand of the transmission line that you see from the left hand side. So that is the transmission line. At the end of the transmission line, there are two other transmission lines. One is a light blue, other is a violet. So that is divided, this transmission line is divided into two parts. This type of transmission line, when it is divided into two parts at a junction, one line divided into two parts at a junction resembles a T. If you look at T and the letter T, so there is one line which comes from the bottom, then at the top it gets divided into two parts. So this is called a T junction. The junction is called a T junction. This is a T junction transmission line. Assume that we have a lossless divider. At the junction, there is no loss. If there is no loss at the junction, the divided lines which have characteristics impedance Z02 and Z03, they are connected at one point to the first line characteristics impedance Z0. Now when the lines are connected at one point, like resistors are connected at one point, means resistors are in parallel. So these lines are connected at one point. If they are connected at one point, the connection is parallel. Therefore, if I look from the Z01 side, then at the junction, the admittance Y in 1, while looking from the left hand side, at the junction, the admittance Y in 1 is equal to the admittance Y02 plus admittance Y03. Y02 is equal to 1 by Z02 and Y03 is equal to 1 by Z03. Therefore, Y in 1, looking from the left side, the input admittance Y in 1 is equal to 1 upon Z02 plus 1 upon Z03. Now, if you want to match this Y in 1 with, or if we want a matching at the junction, then the input impedance at the junction, seen at the junction, should be equal to the characteristics impedance of the line. So Z01, which is the characteristics impedance of the line, should be equal to Z in 1. What is Z in 1? Z in 1 is equal to 1 upon Y in 1. 1 upon Y in 1 is equal to Z02 in parallel with Z03. Z02 in parallel with Z03, that gives you Z02 into Z03 divided by Z02 plus Z03. So Z01, which is equal to Z in 1, is equal to Z02 into Z03 divided by Z02 plus Z03. So this is for matching. If you want the matching at the junction, so the matching gives you this, the first matching for the first line, the matching gives you this. Similarly, we have Y in 3. Y in 1 we have found out what will be Y in 3. Y in 3 will be equal to 1 upon Z01 plus 1 upon Z02. So 1 upon Z01 plus 1 upon Z02, that is equal to Z02 plus Z03 divided by Z02 into Z03 plus 1 upon Z02. Why? 1 upon Z0, as we have seen, Z01 is equal to Z02 into Z03 by Z02 plus Z03. Therefore, 1 upon Z01 is equal to Z02 plus Z03 by Z02 plus Z02 into Z03. So that is for 1 by Z01, then plus 1 by Z02. So that if you do that, then that will be equal to Z02 plus 2 times Z03 divided by Z02 into Z03. So now what we will do is we will take 1 by Z03 common on that into Z02 plus 2 Z03 divided by Z02. Therefore, Y in 3 is not equal to 1 by Z03. Similarly, Y in 2 is not equal to 1 by Z02. So this we have seen. So, but since Y in 3 is not equal to 1 by Z03, Y in 2 is not equal to 1 by Z02, which means they are not matched. 1 by Z01 is equal to 1 by or Y in 1 is equal to 1 by Z01. When 1 by Y in 1 is equal to 1 by Z01, under that condition, Y in 3 is not equal to 1 by Z03 and Y in 2 is not equal to 1 by Z02. So the port 1 is matched, but port 2 and port 3, for port 2 and port 3 or for line 2 and line 3 there is mismatch. So if we match a port at port 1, we cannot match the other ports. This is what we found out from this analysis. Now let us assume that this port 1 is matched. When port 1 is matched, Z01 is equal to Z02, Z03 by Z02 plus Z03. This we have seen in the previous slide. Find out what is the power. Power, input power at port 1, as you know, for power P is equal to 1 by 2 V square by R. That we know from Ohm's law, we know this. P is equal to half V square by R. So use that. So P in 1, so at port 1, the input power is equal to 1 by 2 V1 square by Z01. And at port 2 there is power output, therefore P out 2 at port 2 is equal to 1 by 2 V1 square by Z02. Now we know P in 1 is equal to 1 by 2 V1 square by Z01, which means V1 square is equal to 2P1 by Z0. So put that in the second equation. So P out 2 is equal to 1 by 2 into 2P in 1 2P in 1 into Z01 divided by Z02. So 2 in the numerator and denominator we cancel out. That will give us Z01 by Z02 into P in 1. Similarly, P out 3, that is 1 by 2 V1 square by Z03. Now V1 square is equal to 2P1 into Z01. Put that will give us P out 3 is equal to Z01 by Z03 into P in 1. So we have found out the power at the ports, input power and output powers in terms of input power. How much input power and what is the ratio of the output powers in terms of input power. So if we take the ratio of the output powers, P out 2 by P out 3 is equal to Z03 by Z02, which means if we want to divide power in a particular ratio, then we can choose the characteristics impedance of the lines, output lines. Accordingly, the ratio of the characteristics impedance should be reciprocal of the power outputs along those transmission lines. So we can design the splitter to control the powers going into the two output lines. Now once we have done that, now let us try to examine the reflection at each port. By reflection, what we will find out is S11, S22 and S33. It's a three-port network, so we will find out SII, which is S11, S22 and S33. These three we will find out using the reflection or examining the reflection at the ports. So we have one junction, three ports. At the junction from port 1, suppose the voltage is V1. From port 2, the voltage across the junction, when we consider port 2, is V2. So when we consider the port 3, the voltage is V3 at the junction. So if that happens, then you go to the basic definition of S11 parameter. Similarly, we will go to the basic definition of S22 parameter and S33 parameter. So S11 is equal to V1 minus. V1 minus means the voltage reflected at the junction. So V1 minus along the line 1. So V1 minus divided by root over of Z01 divided by V1 plus divided by root over of Z01, provided A2 is equal to A3 is equal to 0. This is from the definition of S parameter. Now root over of Z01 is common in the numerator and denominator, so that will cancel out. So that leaves us S11 is equal to V1 minus by V1 plus. Also, S11 is the reflection coefficient. The reflection coefficient is Zin minus Z0 by Zin plus Z0. So use that definition. So S11 is equal to Zin1 minus Z01 divided by Zin1 plus Z01. Now Zin1 we have already seen is parallel combination of Z02 and Z03. Here also you can see Zin1 is parallel combination of Z01, Z02 and Z03 at the junction. If we look from the transmission line 1, then on the impedance that we will see is Zin1, which is parallel combination of Z02 and Z03. So Zin1 is parallel combination of Z02 and Z03. So S11 is equal to Z02 in parallel with Z03 minus Z01 divided by Z02 in parallel with Z03 plus Z01, assuming that port 1 is matched, that is that will always be there. We have assumed that port 1 is matched, other ports are not matched. Similarly, S22 will be V2 minus by V2 minus that will be equal to Z01 in parallel with Z02 minus Z02 divided by Z01 parallel with Z03 plus Z02. Similarly, S33 is equal to V3 minus V3 plus V3 minus divided by V3 plus at A1 and A2 equal to 0. That is called 2Z01 parallel Z02 minus Z03 divided by Z01 parallel Z02 plus Z03. Now, when we have a matching at port 1, that will require that Z01 should be less than Z02 and Z03. Because the two lines Z02 and Z03 are combining in parallel, if they will be Z02 or Z03 will be greater than Z01, then there will be no matching. So they have to be less than that. So Z01 is less than Z02 and Z03. Now in these expressions for S11, S22 and S33, the expressions that we have found out, the first term in the numerators must be less than the second terms. If the first term in the numerator must be less than the second terms, that means S22 is not equal to 0, S33 is also not equal to 0. That is the condition. The first terms in the numerator must be less than the second terms. Why? First terms will be less than second terms because Z01 is less than Z02 and Z01 is less than Z03. Using that, the first term will always be less than the second term. Since the first term is less than the second term, therefore S22 is not equal to 0, S33 is not equal to 0. This condition does not apply to the S11 because it can be matched. If it is matched, S11 will be equal to 0. That is possible, but these two are not possible. Also, we already have seen by definition of S parameter, S21 is equal to V2 minus by root over of Z02 divided by V1 plus divided by root over of Z01 when A2 and A3 is equal to 0. So this we can write as V2 minus by V1 plus into root over of Z01 by Z02. Now you know V2 minus by V1 plus. Look at the figure. You can see that at the junction V2 minus is equal to V2 exactly at the junction. From that point it is getting reflected. So at that point, exactly at that point, V2 minus is equal to V2. That is also equal to V1. Therefore, V2 minus by V1 plus is equal to V2 by V1 plus is equal to V1 by V1 plus. Because at the junction, exactly at the junction, V2 minus reflected, there will be the reflected power should be equal to the power at the junction. That's the voltage at the junction under matching condition. So that is what is happening. So V2 minus is equal to V2 is equal to V1 at the junction. Use this. Also, we have V1 by definition. V1 by or V1 is equal to V1 plus into 1 plus S11. This also comes from S parameter. Now, when S11 is equal to 0, V1 is equal to V1 plus. That we know. When S11 is equal to 0 means when there is matching at the port 1. If port 1 is matched, S11 will be 0, then V1 will be V1 plus. There will be no deflection. So V1 minus will be 0, so V1 will be V1 plus. Otherwise, V1 is equal to V1 plus into 1 plus S11. 1 plus S11 will be so V1 plus V1 plus into S11. V1 plus into S11 is actually V1 minus, because S11 is equal to V1 minus by V1 plus. So V1 is equal to V1 plus into 1 plus S11. So that we can write as V1 by V1 plus. Also, sorry, that implies that V1 by V1 plus is equal to 1 plus S11. So V1 by V1 plus is equal to 1 plus S11. Now S21 will be equal to V2 minus by V1 plus. V2 minus by V1 plus is equal to V1 by V1 plus, and V1 by V1 plus is equal to 1 plus S11. Therefore, S21 is equal to V2 minus by V1 plus into root over of Z01 by Z02, that is equal to 1 plus S11 into root over of Z01 by Z02. So we have found out the expression for S21. Now the network is reciprocal. So since it is reciprocal, therefore S21 is equal to S12. So we have found out expression for S12 also. Once we find out the expression for S21, we have found out the expression for S12 also. Similarly, following a similar procedure, we can find out what is S31. S31 will be 1 plus S11 into root over of Z01 by Z03. That will be equal to S13. Similarly, S32 will be equal to S23. That will be equal to 1 plus S22 into root over of Z02 by Z03. So this is about the S parameters of the power divider. So we have found out all the expressions for the S parameters for the power divider. Now we are continuing with port 1 match. Port 1 match means Z01 is equal to Z02, Z03 divided by Z02 plus Z03. Also, matching implies that S11 is equal to 0, S22 is equal to Z01 parallel Z03 minus Z02 divided by Z01 parallel Z03 plus Z02. Similarly, the expression for S33. Also, we have seen this S21 is equal to S12 is equal to 1 plus S11 root over of Z01 by Z02. That we can write as root over of Z01 by Z02 because S11 is equal to 0 under the matching of port 1. So putting that, this is equal to root over of Z01 by Z02. Now put the expression for Z01, which is Z02, Z03 by Z02 plus Z03. Putting that, we get root over of Z03 by Z02 plus Z03. Similarly, S31 is equal to S13 is equal to root over of Z02 in the numerator divided by Z02 plus Z03 in the denominator. Now, from the last slide, we have seen S32 is equal to S23 is equal to 1 plus S22 into root over of Z02 by Z03, which implies that port 2 and port 3, they are not isolated. There is some relationship between port 2 and port 3. They are not isolated. So some power at port 2 is related to power at port 3. Power at port 3 is related to power at port 2. They are not isolated. Only S11 is equal to 0. S is equal to, now you can find out what is the expression for S parameter. The S matrix, you can see now it is not reciprocal because it is reciprocal, but it is not matched at all ports. So S2, only S11 is 0, so one port is matched, other ports are not matched. And we have found out what are the expressions for all these ports. Okay. This is a simple example in the microstrip form of a T-junction power divider. So we have a 50 ohm transmission line and it is connected to 200 ohm transmission lines. As you know, if I connect 200 ohms resistors in parallel, that will be equal to 50 ohm. So therefore 50 ohm transmission line here is connected to 200 ohm transmission lines which are connected in parallel at the junction. So Z01 parallel Z02 is equal to Z01 parallel Z03, that is equal to 50 parallel 100, which is equal to 33.333 ohms. Now from this you can say S11 is equal to 0, S22 is equal to S33 is equal to minus 1 by 2. This you have to find out using the expressions that we have found out earlier. S21 is equal to S12 will be equal to root over of 1 by 2. S31 is equal to S13 is equal to root over of 1 by 2. And S32 is equal to S23 is equal to 1 by 2. So these are the S parameters for a microstrip T-junction power divider given here. The same thing works as a matched power combiner. This also you can see that equal waves are incident from port 2 and port 3. If you incident equal waves from and port 3, they will combine. So when they are equal, A2 is equal to A3, and you can find out what is V3, which is equal to A1 into S31 plus A2 into S32 plus A3 into S33. A2 is equal to A3, take A3 common. A1 will be 0 because of matching. So take A3 common. That gives you A3 into S33 plus S32, and S33 and S32 are minus half and half. So from that you see that V3 is equal to 0. So there is no reflection if equal waves are incident on port 2 and port 3 while port 1 is matched. So this is a combiner. Then we will come to something called equal split or 3 dB power divider. So we considered a power combiner example. Now whatever power we are giving at port 1 is to be divided equally between power 2 port 2 and port 3. Whatever power we will get at port 2 should be equal to the power at port 3. But the condition is the power at port 2 and power at port 3, when we combine them, they may not be equal to the power given at the input. So this type of the power divider that we are going to consider is called a Wilkinson power divider. The Wilkinson power divider can also be designed to have unequal splits. We are considering the equal split here. In your book there is equal split power divider, so we are considering the equal split power divider. Now you can see on that there is slight change here. What is the change? We have a transmission line with characteristics impedance Z0, that is transmission line 1. Then we have two other transmission lines with characteristics impedance also as Z0. So those are transmission line 2 and transmission line 3. All the transmission lines are black. You can see the black color. These are the transmission lines. Then between the transmission line 1 and the transmission line 2, or transmission line 1 and transmission line 3, there is another transmission line of characteristics impedance root 2 into Z0, and the length is lambda g by 4. So on that much of length, lambda g by 4 length, and characteristic impedance root 2 Z0. Then the third condition is between the transmission line 2 and transmission line 3 there is a lumped resistor. The resistance of the lumped resistor is 2 times Z0. So there are few things that you should remember. There are 3 transmission lines, each of characteristics impedance Z0. Transmission line 1 is connected to transmission line 2 and transmission line 3. In between the connection there is a lambda g by 4 transmission line of characteristics impedance root 2 into Z0. Between transmission line 2 and transmission line 3 there is a lumped resistance of lumped resistor of resistance 2 Z0. If you have such a power divider, then the power is equally split between port 2 and port 3, or you will get equal powers at port 2 and port 3. In this case, the beauty of this is all ports are matched. So S11 is equal to S22 is equal to S33 is equal to 0. If you have such a design, then output ports are isolated, which means S23 is equal to S32 is equal to 0. There is no relationship between S23 and S32. They are equal to 0. No power is lost in going from port 1 to port 2 and port 3, which means S21 square is equal to S31 square is equal to 1 by 3. Sorry, 1 by 2. No power is lost. So S12 square, S21 square plus S31 square is equal to 1. That is satisfied. Both of them are equal to half. Now this matrix is not unitary. The S parameter of this Wilkinson power divider is not unitary. That is what is important to note. So S matrix of the Wilkinson power divider will be of the form minus j by root 2 into 0 into the matrix with elements as 0 1 1 1 0 0 and then 1 0 0. So this is not unitary matrix. Now we are going to analyze and find out this S parameter of the Wilkinson power divider. And that we will do the analysis of Wilkinson power divider. We will do that. We will do the analysis using even odd mode analysis that we discussed in the last class. So we are going to use what we discussed in the last class, even odd mode analysis, that will be used to analyze the Wilkinson power divider. This requires, as we saw in the last class, 2 separate analyses. One is even mode analysis, one is odd mode analysis. Finally, we will add these results. Each analysis will involve only a 2-port device instead of a 3-port device. On this we have seen in the last class, when you do even odd mode analysis, it is applicable for 2-port devices. So 3-port device is to be divided into a 2 2-port devices, and we will do the analysis. That we will do after the break. We will take a lunch break. When we come back from the lunch break, we will do the even odd mode analysis of the Wilkinson power divider and find out what are the S parameters using the even odd mode analysis. Hopefully you have understood up to this point. From this point we will proceed forward after the lunch break. So we will start exactly at 2:30. do not delay. We have lost about 10-15 minutes. So that we will make up after the launch. I have taken your attendance for this class. After the launch also I will take attendance for that.